You see, since we've exhausted our repertoire of, well, Greek, Arabic, Phoenician, and also Hebrew letters, we can finally start using the real stuff, the good stuff. We can finally make use of Japanese kanji and Chinese symbols.
Today we're going to do the cylindrical and spherical analogs of the work that we did 2 days ago when we were looking at the graphs of some quintessential three-dimensional surfaces and their associated equations. Once again, this is going to be incredibly useful for 254 when you will be called upon on a regular basis to describe surfaces and the region between two surfaces in the most convenient way possible. By the end of today, we should be able to convert equations between the spherical, cylindrical, and rectangular coordinate systems. And we should be able to identify the graph and equation of some common surfaces in the cylindrical and spherical coordinate systems, including spheres, cones, planes, paraboloids, and cylinders. Now, today's material is probably going to be a little bit on the short side because we're not learning any really new procedures, we're not learning any new formulas, we're not learning any new concepts. We're just trying to get some practice with those formulas, ideas, and concepts in a few specific cases. So the purpose of this video is just to give you an example of how I tend to think about a few example exercises, and then we'll hopefully have lots of time today for you to get some practice with this material on your own. The first thing that I want to do for practice with these coordinate systems is to look at the shape that is formed by each of the following equations as graphed in three-dimensional space. So here we have the rectangular coordinates. What happens if we just specify that x has to be a given constant? What if we only specify that y is fixed? What if we specify that z is fixed? What kind of shape is formed by those requirements? Then, moving into the cylindrical coordinate system, what kind of shape do we get if we only specify that r must be equal to a fixed value? What kind of shape do we get if we only specify that theta must be equal to a fixed value? And finally, moving into the spherical coordinate systems, what kind of shape do we get if we specify that rho must be equal to a fixed value? And what kind of shape do we get if we specify that phi must be equal to a fixed value? Now remember what a graph is. A graph is the set of all the points that satisfy the equation that's given to you. So when someone says that x must be equal to c, they're saying that a point is on the graph as long as the x value is equal to this given constant number c. The values of y and z have no impact on the truth value of this equation. So let's suppose that x equals c is located out here somewhere, maybe a couple of units away from the origin in the positive x direction. As long as the x is equal to this value, the point can have any z value, any y value. So as a result, the set of points which satisfy the equation, the graph of this equation, forms a plane. We can also see this from the equation itself. One way to think about this equation is as 1 times x minus c plus 0 y's plus 0 z's equals 0, which we can recognize as the equation of a plane containing the point c0, 0 with a normal vector given by 1, 0, 0. Correspondingly, we have y equals c, which is very similar, except this time the y is specified and restricted to a single number, and it's the x and the z which are allowed to be free. Put another way, going back to our work on equations of planes, if we rewrite this as 0x plus 1 y minus c plus 0z equals 0, subtracting c from both sides, then we can recognize this as a plane which contains the point where y is equal to this given constant, with a normal vector which is pointing in the y direction. As a result, we get a plane similar to the xz plane with its edge facing us, standing up with its edge facing us, passing through the point 0, C0. And very similarly for z as well. Z equals c is going to give you a plane which passes through the point where everything is 0 except for z, with a normal vector pointing straight up, which causes the plane to lie horizontally flat, just like the xy plane. Using some more of that language from when we studied planes, the plane x equals c is parallel to the yz plane. Y equals c is parallel to the xz plane. Z equals c is parallel to the xy plane. Now let's consider r equals c. R equals c, or if you prefer, the square root of x squared plus y squared equals c. In this case, we know that the value of z is free. The height of the point can be whatever it wants to be, but as long as the x and y coordinates satisfy this equation, then the point will be on the graph. We recognize this as the equation of a cylinder, which we studied in rectangular coordinates 2 days ago. X and y must live on a circle of radius c, which is then extended infinitely in the positive and negative z directions to reflect the fact that the value of z is free in this equation. As a result, we get the graph in the shape of a cylinder of radius c centered around the z-axis. If the polar coordinate r is equal to a constant, then the shape formed by that is a cylinder centered at the z-axis of radius c. Now, what kind of shape do we get if the other cylindrical coordinate is equal to a constant? If theta is equal to c. If theta is equal to c, then the only condition that needs to be satisfied by the point on your graph is that its angle with the positive x-axis has to be c radians. Because of that, neither the point's height nor the point's distance from the origin really matter at all. So if I try and describe all the points which have this specified angle, well, if we describe those points just in terms of x and y values, all the points with the specified angle, regardless of the value of r, would form a ray. However, in three-dimensional space, I'm also free to extend that ray infinitely up and down. Z is also free, so that ray gets stretched out infinitely in the positive and negative Z directions. Which means that that ray gets converted in 3D to what's called a half-infinite plane. The plane has one edge, which is located on the z-axis itself, but then it can extend infinitely in the direction of the ray. Now what about rho equals c? And we did see an example of this yesterday. Rho equals c occurs when the square root of x squared plus y squared plus z squared is equal to this constant. So in other words, this is satisfied by any point whose distance from the origin, as measured in three-dimensional space, is equal to this constant c. And such a point is located on the sphere of radius 3, centered at the origin. Now, one of the most interesting examples of coordinate equals constant is this case of what if the spherical coordinate phi is constant? What kind of shape is formed by that? Now this describes any point whose angle with the positive z-axis is equal to phi. The three-dimensional distance of the point from the origin doesn't matter. And the point's longitude, its horizontal orientation, its theta value, also doesn't matter. Let's just say that this is c, measured downward from the positive z-axis. Because the value of rho doesn't matter, I can be as far away from the origin as I want to be. I can be rho equals 0, which is on the origin itself, or I can be anywhere along this ray extending from the origin corresponding to this angle phi equals c. But not only that, because the angle of theta doesn't matter, I can spin this ray around in any horizontal direction I like, and I can point it along any longitude that I like. So I could travel along that ray in the negative y direction, but I could just as well travel along that ray in the positive y direction, or positive x, or negative x, or any horizontal direction I choose. So because I can travel in any horizontal direction for any distance I like, the shape that is formed is a cone. A cone is the shape formed when phi is a specified angle and the other variables are free. Phi equals constant corresponds to a cone. The wideness of that cone depends on how large your angle phi is. If phi is small, then the cone is going to be quite narrow and close to the positive z-axis. If phi is equal to a very large number, something that's close to 90 degrees, then the cone is going to be incredibly wide, almost planar. Note that if phi happens to be even larger than 90 degrees, then the cone is going to open downward. If phi is greater than 90 degrees, then we're operating with points that have a negative z coordinate, that are in the southern hemisphere. So such a graph would be a cone opening down if your phi value is that large. So let's get some practice describing not entire spheres, but this portion of a sphere using cylindrical for 3D, cylindrical and spherical coordinates. All right, so we have z is equal to the square root of 16 take away x squared take away y squared. Now, when I'm converting this to cylindrical, I'm always looking for opportunities potentially to use the fact that x squared plus y squared equals r squared. Because cylindrical coordinates, as we noted yesterday, are really conducive to converting equations which contain this quantity, x squared plus y squared. So let's take the equation of our upper hemisphere and rewrite it slightly. Z equals the square root of 16 take away the sum of x squared plus y squared. Now that quantity that we're looking for has appeared, and we can rewrite the hemisphere in cylindrical coordinates in the following way. It could also be expressed as the square root of 16 minus r squared. Question, can this be simplified anymore? Can this, for example, be rewritten as z equals 4 minus r, where we simplify the square root of 16 and the square root of r squared separately? No, 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 no. Please be careful. I see this error quite a bit when folks are getting a little bit stressed in Calc 3 and 4. I think that this is what people do when they're under pressure. They make this mistake of trying to take the square root of two individual terms underneath a radical symbol. However, when you have an addition or subtraction under a root, as a rule, you cannot simplify that root unless you can do something wacky with factoring. You're going to have to leave it in this format. Z is equal to the square root of 16 take away r squared. That is as simple as this quantity can become. Now, what if we were going to try and describe an upper hemisphere using spherical coordinates? For the spherical coordinate system, we're generally looking for the appearance of the quantity x squared plus y squared plus z squared, because we know that that can be converted to rho squared in spherical coordinates. Now, that quantity is not showing up explicitly right now, but if we take this equation and square both sides, then we might be able to get it to appear. Do a little rearranging, and we get x squared plus y squared plus z squared equals 16. We get rho squared equals 16, which gives us rho equals 4. Now, what do you think? Can I stop there? Is the set of all points that satisfies the equation rho equals 4 the same thing as the upper hemisphere, where z is equal to the positive square root of 16 minus x squared minus y squared? Remember from the previous page that when rho was equal to a constant, we got the full sphere of radius 3 centered at the origin. Or in general, I should say, of radius c centered at the origin. However, in our problem, we don't have the entire sphere. we only have the half of the sphere where the z has a positive value, which means that rho equals 4 by itself is not complete. We need to add some extra conditions to the equation rho equals 4 in order to ensure that we only get the part of the sphere where the z values are non-negative. Now z greater than or equal to 0 corresponds to the northern hemisphere. Where the values of phi, which measure the point's angle with the positive z-axis, the values of phi are pretty small. We haven't descended that much from the positive z. We haven't descended that much from the North Pole. So if the value of phi is less than 90 degrees, in that case we will only get the portion of the graph which is above the xy plane, which is in the northern hemisphere. So the final answer would consist of these two pieces of data together. The equation corresponding to the upper hemisphere would be that the rho value has to be equal to 4, and we also require that the phi value does not exceed 90 degrees. These two together give you the upper hemisphere. Let's go ahead and describe the cone in polar and spherical coordinates. The cone where we have z equals the square root of x squared plus y squared. Once again, this should say cylindrical because this is in three-dimensional space. Cylindrical is for 3D, polar is for 2D. Now, cylindrical gives me the opportunity to use the conversion x squared plus y squared equals r squared. So if I make that substitution and then simplify, the equation of this cone in cylindrical coordinates is going to be fairly simple. The z value always has to match the r value. What about spherical coordinates? From our work on the previous page, we can actually expect that the equation of this cone in spherical coordinates is probably going to have the equation phi equals a constant, because the equation phi equals a constant was the spherical expression of a cone with its vertex at the origin. So the question is, which constant will be appropriate for the cone in this problem? To see that, it can actually be useful to use the cylindrical equation. Because we have a formula that can be used to convert r from cylindrical coordinates to spherical coordinates. R was equal to rho times sine of the angle phi. Z was equal to rho times cosine of the angle phi. So if I cancel the two rows, this is telling me that cosine phi is a match to sine phi. And for phi between 0 and 180 degrees, this only occurs at one value of phi. These two quantities match when phi is equal to 45 degrees, or pi over 4 radians. So that's the constant, and therefore the equation of this cone in spherical coordinates is equal to pi over 4. Now the last couple of examples that I'm going to show you, which will be very close to the kind of stuff that you will be looking at in Calculus 4. Let's look at the surface which is formed by graphing each of the following equations in three-dimensional space. Now, when faced with an exercise of this variety, I tend to try one of two approaches. The first thing that I tend to try and do is check to see if I can use my graphical and conceptual understanding of the meaning of the coordinates to describe the surface. However, all of the exercises in this section I think are too complicated to take that approach directly at the beginning of the problem. That approach worked well for really simple equations like we saw in the very first exercise from today's material. But these equations are way more complicated. R equals 4 cosine theta, R equals square root 4 minus z squared, R equals 3 over cosine phi. All of these equations are too complicated for me to look at them and know right away what shape is going to be formed. So, if you're having trouble understanding a surface as described in one coordinate system, it can be useful to try and convert it to a different coordinate system. Oftentimes, it can be useful to try and convert the equation back into XYZ, rectangular coordinates, because we are so much more familiar with rectangular coordinates than we are with the other coordinate systems. For example, here we have r equals 4 cosine theta. Now I have an r, but if I try and convert that r back into rectangular coordinates, I'm going to get a huge mess with the square root of x squared and y squared. Likewise, cosine theta all by itself could not be easily converted into something containing an x and a y. However, if I multiply both sides by an extra copy of r, it solves both of my problems. If I do this, that r becomes r squared, and that cos becomes r cos theta. R squared can be very easily converted to rectangular coordinates. It's just x squared plus y squared. And r cos theta is also easily expressible in rectangular. That's just 4x. Now, this equation is going to begin to look a little bit more familiar. This is starting to look like the equation of a circle. The center of the circle is not immediately apparent because this equation is not currently in standard form. But if we complete the square by taking half the coefficient of x, squaring it, adding it to both sides, and then factoring, this is equivalent to x minus 2 quantity squared plus y squared equals 2 squared, which in two-dimensional space would be a circle of radius 2 centered at the point 2, 0. But bear in mind that this equation is living in three-dimensional space, which means that this equation is not that of a circle. It's that of a circle that's been extended infinitely in the positive and negative z directions. As a result, that circle in 2D gets transformed to a cylinder in 3D. Not a cylinder centered around the z-axis, but this is a cylinder that's been displaced slightly and moved a little bit in the positive x direction. We could take a similar approach here. We have r equals the square root of 4 minus z squared. I don't recognize this equation, but let's see if it becomes more familiar if I express it in an alternative coordinate system. For example, rectangular. If I square both sides to get an r squared, I replace r squared with x squared plus y squared, and I can rearrange this into the equation of a sphere. radius equals square root of 4 minus z squared can be rewritten as x squared plus y squared plus z squared equals 2 squared, which is a sphere centered at the origin of radius 2. Not the upper hemisphere, not the lower hemisphere, but the full sphere. Because r is always positive, so defining r as the positive square root of 4 minus z squared is not putting any abnormal or unusual restrictions on the points that are allowed on this surface. I also don't recognize this quantity, rho equals 3 divided by cosine phi, currently expressed in spherical coordinates. But let's try converting it to an alternative coordinate system, such as rectangular. Now, once again, just a raw rho with no square can be annoying to convert to rectangular coordinates because you would need a square root. Likewise, cosine phi would be really annoying to convert to rectangular as well. But if I rearrange this equation slightly and I clear the fractions, then I get rho times cosine phi, which all of a sudden is part of one of the conversion formulas that I had. Rho times cosine phi is equivalent to z equals 3. Z equals 3, which is the equation of a plane with a height of 3 parallel to the xy plane. Z equals constant, z equals 3 is just a plane. Correspondingly, what if we had the equation rho equals 3 divided by sine phi? This time, if we clear the fractions, I recognize rho sine phi. Oh, it's doing it again, folks. It's eating pen strokes. This formula on the left side, and it's gone. Alright, this time, this time I'm going to pause the video and actually reset this thing. Hold on. Alright, what was I saying? I was saying that if you clear the fractions, rho sine phi, then once again we get the appearance of one of the quantities from our conversion formulas. Rho cosine phi was the same thing as z. Rho sine phi was the same thing as r. So this is equivalent to r equals the constant 3, and we recognize this as the cylindrical equation, once again for a cylinder, radius 3, which is centered around the z-axis. For a final example of the kind of thought process that I would use to understand the graph of a spherical equation, we have rho equals 6 sine phi. In spirit, this is very similar to the very first equation that we did, where we had r equals 4 cosine theta. Converting r by itself, likewise converting rho by itself, is kind of a pain. But if we had an extra copy of rho, that would give us a rho squared, which is much easier to convert. Converting cos phi is a huge pain also. But if I just had an extra copy of rho on the right-hand side, then I would have rho cosine phi, and that could be converted to z. So what I'm going to do is I'm going to multiply both sides by rho to fix both of my problems. That way I get a rho squared on the left and a rho cos phi on the right, which can be converted to x squared plus y squared plus z squared equals 6z. Now let's go ahead and take this equation and complete the square. Take half the coefficient of z, square it, add it to both sides so that you can factor, and just like I had an offset cylinder in the very first example, in this case I have a slightly offset sphere. This is a sphere of radius 3, but not centered at the origin, centered at the point where x is 0, y is 0, and z is 3. To sum up what we did today, we practiced using our understanding of the coordinate systems and their graphical meaning and the formulas for conversion between those systems to understand all kinds of different equations and to determine the graph that was formed by those equations. We looked at some simple cases of what if the coordinate is equal to a constant, and we looked at some more complicated examples such as cones, such as spheres, such as planes, described in terms of the spherical and cylindrical coordinate systems. We got a better understanding of those equations by manipulating them so that they could be rewritten in another coordinate system, usually in the rectangular coordinate system.